What if you could take a trip to the most extreme place in the universe? A place where the laws of physics aren't just bent, they're pushed to their breaking point. Imagine you're on a mission to the edge of the universe. A short, 1-hour trip to orbit a black hole and collect some data. Just 60 minutes. But when you get back, you discover everyone you've ever known, everyone you love, has been gone for 1,000 years. Sounds like science fiction, right? But it's not. It's the bizarre, mind-bending reality of gravitational time dilation, a secret of the cosmos that messes with our whole understanding of existence. What if I told you the universe has natural time machines, places where the river of time slows to a crawl? These aren't fantasies, they're black holes. And the journey to understand them starts not in the depths of space, but with the force we feel every single second of our lives: gravity. How can something so familiar hold the key to something so strange? To find out, we have to unravel the story of how our picture of the universe was turned completely upside down. To really get why black holes mess with time, we have to rewind a bit. For centuries, our picture of the universe came from Isaac Newton. He imagined space as a fixed, rigid stage where things moved, and time as a universal clock, ticking at the same rate for everybody, everywhere. It was a neat, orderly, and comfortable way to see things. But in 1915, a patent clerk named Albert Einstein came along and basically tore that picture to shreds. Einstein's big idea was that space and time aren't separate things at all. They're woven together into a single, four-dimensional fabric he called spacetime. This was the core of his theory of general relativity, and it completely flipped our understanding of gravity. Einstein said gravity isn't some mysterious force pulling us down, it's just what happens when mass and energy warp the fabric of spacetime. The classic analogy is a trampoline. Imagine space-time is a stretched rubber sheet. If you put a marble on it, it makes a tiny little dent. Roll another marble nearby, and its path curves slightly. Now, plop a heavy bowling ball in the middle. It creates a deep, dramatic well in the sheet. A marble rolled nearby will now spiral right in, not because the ball is pulling it, but because it's just following the curve in the sheet. That's pretty much how gravity works. The sun, being massive, creates a big curve in space-time, and planets like Earth are just following those curved paths. We call them orbits. The Earth creates its own little warp, which is why we're all stuck to the ground. Even you are warping space-time just a tiny, tiny bit right now. But here's the kicker. Warping space is only half the story. Because space and time are linked, when you curve space, you also curve time. Time is a dimension, just like up, down, left, and right. Where gravity is strongest, the path through the time dimension gets stretched out. This leads to one of the wildest predictions of general relativity: gravitational time dilation. It means time literally runs slower in stronger gravitational fields. And this isn't just a theory, it's real. Clocks on GPS satellites, which are farther from Earth's gravity, tick just a little bit faster than clocks down here. Engineers have to constantly correct for it, or your GPS would be useless in minutes. So if that tiny difference in gravity can mess with time, imagine what happens when you introduce something with gravity so insane it can warp space-time to its breaking point. And that's where black holes come in. So what exactly is a black hole? Imagine a cosmic vacuum cleaner silently lurking in the depths of space. That's a black hole, an object so dense that nothing, not even light, can escape its grasp. But what if I told you that these mysterious giants do more than just suck up everything around them? They actually bend time itself. To understand how black holes warp time, we must turn to Albert Einstein and his theory of general relativity. According to Einstein, massive objects like black holes distort the fabric of space-time around them. Think of space-time as a rubber sheet. Placing a heavy bowling ball on it creates a deep dip. The greater the mass of the object, the deeper the dip and the stronger the pull. Now, when you approach a black hole, the effects become more dramatic. You might feel time slowing down relative to someone watching from a safe distance. This phenomenon is called time dilation. If you were to hover near a black hole, you could experience what feels like minutes, while years could pass for someone far away. Isn't that mind-boggling? So why does this happen? It's all about gravity. A black hole's immense gravitational pull affects the flow of time, stretching moments into eternity. That's why black holes are sometimes dubbed time machines. They provide a unique glimpse into the nature of reality, where time is not a constant, but a malleable dimension. Understanding how black holes bend time gives us insight not just into the cosmos, but into the very essence of existence itself. The universe is full of mysteries, and black holes are among the most fascinating of them all. All right, let's get back to our spaceship heading towards Sagittarius A star. We've left the gentle curves of our solar system and are now approaching the abyss. Out here, time for us and time on Earth are pretty much the same. But as we get closer, the fabric of space-time around us gets more and more warped. We're heading deep into a gravity well, and this is where gravitational time dilation kicks into high gear. To our friends at Mission Control, our clock would look like it's starting to slow down. It's not broken. Our path through the dimension of time is literally being stretched by gravity. But inside our ship, everything feels totally normal. Our heart beats once per second, coffee takes 5 minutes to brew, a movie is still 2 hours long. To us, time feels like time. The shock comes when we try to talk to anyone else. Let's say we spend what feels like 1 hour exploring. We send a message back to Earth. Mission clock reads 1300. Everything's great. The reply would be baffling. Copy that. Your signal arrived at 600 hours Earth time. It's been 5 hours here. Can you confirm? As we get even closer, the effect becomes insane. Let's push our ship to just outside the photon sphere, a region where gravity is so strong that light itself is forced to orbit the black hole. Here, the time dilation is off the charts. For every minute that passes for us, years could be flying by on Earth. We could watch a distant star be born, live its entire life, and die in what feels like a few moments. Looking out at the universe would be like watching a film on fast forward. We'd see galaxies spin and nebulae dance over cosmic timescales, all during what feels like a lazy Tuesday afternoon. This is the famous twin paradox cranked up to 11. If you flew near a black hole for what felt like a few years and then came back, you would find that centuries or even millennia had passed on Earth. You would have effectively bought a one-way ticket to the distant future. This all comes directly from Einstein's picture of space-time. Time isn't universal. Its flow is relative, and it's tied to gravity. The stronger the gravity, the slower time flows for you compared to someone far away.
We've seen the journey from the traveler's point of view, where the universe outside speeds up. But now for the really mind-bending part. What does the observer back on Earth see? What does Mission Control witness as our ship gets closer and closer to the event horizon? From their perspective, the scene is completely different, and maybe even weirder. As our ship dives deeper into the gravity well, the light from our ship has to fight its way out. This intense gravity steals energy from the photons of light, stretching their wavelength and shifting them toward the red end of the spectrum. This is called gravitational redshift. At first, it would be subtle. Our shiny white ship might look a bit orange. But as we got closer to the event horizon, the redshift would become extreme. Our ship would fade from white to orange to deep red, then to infrared, and finally to radio waves. We would literally fade from sight. At the same time, Mission Control would see our clocks slowing down. They'd see us moving in slow motion. Our transmissions would arrive hours, then days, then years apart. As we approached the event horizon, our ship would seem to grind to a halt. And here's the paradox. From the outside world's point of view, our ship will never cross the event horizon. We will appear to slow down, get redder and dimmer, and look like we're frozen in time right at the edge, like a fly trapped in amber. Our image would be smeared across the event horizon, slowly fading over an infinite amount of time. To the rest of the universe, we'd effectively just vanish. So who's right? The traveler who feels themselves cross the event horizon without any drama? Or the distant observer for whom that crossing takes forever and never really happens? The stunning answer from relativity is they're both right. Reality depends on your frame of reference. For the person falling in, the trip across the horizon is quick, followed by a not-so-great encounter with the singularity. For everyone else, that final moment is postponed for eternity. The event horizon isn't just a boundary in space, it's a boundary in time, where your future is cut off from the rest of the universe. As if all that wasn't weird enough, black holes have another trick. We've mostly been talking about a simple, non-rotating black hole, but in the real universe, things spin. When a massive star collapses, that spin gets amplified, a lot. This means most black holes are probably spinning, and that changes everything. A spinning black hole doesn't just warp space-time, it drags it around like a cosmic whirlpool. This is a real phenomenon called frame dragging. Think of stirring honey with a spoon. The honey right next to the spoon gets dragged along for the ride. A spinning black hole does that to the fabric of reality itself. As our ship approaches a spinning black hole, we get caught in this vortex. Even if we pointed our engines straight ahead, we'd be irresistibly pulled into orbit, forced to spin in the same direction as the black hole. And the closer we get, the more powerful it is. There's a region called the ergosphere, and inside it, The dragging of space-time is so intense that standing still is impossible. You'd have to move faster than light against the current to stay in one place, which you can't. Everything in the ergosphere is forced to spin. And this isn't just a theory. Frame dragging has actually been measured around our own spinning Earth by the Gravity Probe B satellite. Astronomers also see its effects in the swirling disks of gas and dust orbiting supermassive black holes. In fact, recent observations suggest Sagittarius A star is spinning rapidly, meaning the center of our own galaxy is a swirling vortex of space-time. For our trip, this just adds another layer of chaos. We're not just falling into a pit, we're being swept up in a space-time current. Our path is no longer a straight plunge, but a dizzying spiral, dictated by the black hole's spin. It's one last powerful reminder that near a black hole, the stage of reality isn't just sitting there, it's a violent, active part of the show. This trip to the edge of reality shows just how bizarre and flexible space-time can be. Time dilation, the observer paradox, frame dragging, these aren't just fun ideas from science fiction. They are real predictions of Einstein's theory of general relativity, a theory that's passed every test we've thrown at it for over 100 years. If you find this stuff as fascinating as we do, hit that subscribe button and ring the notification bell so you don't miss our next dive into the cosmos. And let us know in the comments, what's the one thing about black holes that just completely blows your mind? Our journey to a supermassive black hole has shown us a place where gravity completely overwhelms our sense of time. We've seen that for a traveler, time can slow to a crawl, offering a one-way ticket to the future. We've seen the paradox from the outside, where that same traveler is frozen at the edge of the abyss for eternity. And we've seen how spinning black holes turn space-time itself into a raging whirlpool. Black holes are more than just cosmic oddities. They are nature's ultimate laboratories. They push our understanding of physics to the absolute limit, revealing a universe that is far stranger and more wonderful than we could ever imagine. They force us to accept that there are no universal clocks, no fixed stage, only the dynamic, curving, and twisting fabric of space-time. And as we keep staring into these dark hearts of galaxies, we're not just learning about them, we're learning the fundamental rules that govern our entire universe.